To start with, we can check that the necessary materials for the simulation are available in the material database. Open the material database by clicking on the Materials button in the main toolbar. The list of available materials is displayed in the material list. We will be using gold, glass, and etch materials. Click on a material to see the material data in the Material Properties section of the material database. The etch material is a material with refractive index 1, and we will use this material to represent the etched holes in the gold film. If the background index was not 1, then the refractive index of the etch material would need to be modified to match the background index. We will use the materials available in the default material database, so it's not necessary to add any new materials. The next step is to set up the structures. Add a rectangle from the Structures drop-down menu to represent the gold film. Click the arrow next to the Structures button to open the menu. Edit the rectangle. There are several ways to open the edit window. You can do this by selecting the object in the object tree and clicking on the Edit button in the toolbar on the left, or you can use the Edit menu in the title bar menu. Here you can see that the keyboard shortcut to edit an object is E. Finally, you can also right-click on the object and select Edit Object from the context menu. Set the name of the structure to Film. In the Geometry tab, set the X and Y position to 0 and span to 1.2 microns. The period of the device is 0.4 microns, so this will represent 3 periods in each direction. To set the device thickness, set the Z-min position to 0 and Z-max position to 0.1 micron to simulate a 100 nanometer thick film. In the Material tab, use the drop-down menu to select the AU Gold CRC material. Make a copy of the rectangle using the copy and paste keyboard shortcuts. Change the name to Substrate. Set Z-max to 0 and Z-min to -1 micron, so the rectangle will be 1 micron thick. In the Material tab, set the material to SiO2 glass Palic. Next, add an array of circles from the object library to represent the array of holes etched in the gold film. The object library contains a library of structure groups that can be used to set up more complex structures such as periodic arrays. If the object library window is not already open, you can open it from the View, then Windows menu. Under the Category drop-down in the object library, select Photonic Crystals. Then, under the Object list, select Rectangular Lattice PC Array, and click Insert to insert the selected object. You can see the new structure group called Rect PC in the object tree. Edit the structure group and set the name to nanoholes. Under the User Properties table, double-click to set the material of the circles to etch. Then set the Z-span property to 0.1 micron and the Z position to 0.05 micron to match the position of the gold film. The NX and NY properties set the number of periods of the array to set up in the X and Y directions. Set these to 3. The AX and AY properties set the period in the X and Y directions. Set these to 0.4 micron. Finally, set the radius to 0.1 micron. You can also check the comments at the top of the script to see the definitions of the user properties. Now check the structure in the viewports to make sure it looks like what we expect. We can zoom into the structure and select each object in the object tree to highlight the object in the viewport. We have a gold layer above the glass substrate with an array of holes etched in the gold film. We have set up a 3x3 array of nanoholes However, it is sufficient to simulate one unit cell in the solver region and use periodic boundary conditions in order to simulate an infinitely periodic structure. We'll add and set up the solver region next. Use the Simulation drop-down menu to add a simulation region. The General tab is where you can set the dimension of the solver region, background index, which is used anywhere where no structures are defined, and the simulation time and temperature. We can use the default settings here. Under the Geometry tab, set the X position to 0 and X span to 0.4 micron to match the period of the device. Do the same for the Y position and span. The simulated period is set by the simulation region span, so it should be set to match the period of the structure. Set the Z position to 0 and Z span to 1 micron. Under the Mesh Settings tab, we can set the Mesh Generation method and Mesh Refinement method. The default settings are usually sufficient for initial simulations, so we won't make any changes here. We can increase the mesh accuracy setting in the convergence testing stage when we want to get final high accuracy results. Under the Boundary Conditions tab, set the X and Y boundary conditions to periodic. Use the PML absorbing boundary conditions in the Z direction, which is above and below the structure. Under the PML settings table, double-click to set the profile to steep angle. The steep angle PML profile is recommended when simulating periodic structures, since light might be diffracted to grading orders propagating at an angle, and the steep angle profile is more efficient at absorbing light incident at an angle. You can click on the Help Me Choose PML Settings link for more tips on setting up the PML settings. Click OK to accept the settings. We can now see the simulation region. Use the Zoom Extent button to zoom the viewports around the simulation region. The simulation region has blue boundaries indicating the periodic boundaries in the X and Y directions, and orange boundaries indicating the PML boundaries above and below. We can use the ruler tool to check that the Z span of the simulation region is large enough. A rule of thumb is that we want there to be a distance of at least half a wavelength of uniform material in front of the PML. Since we will be simulating a wavelength up to 0.7 microns, we want to measure a distance of at least 0.35 microns of air above the structure and glass below. Click and drag in the viewport, and the measured distance is displayed below. Also notice that the substrate extends into the PML boundary below, so any light that travels through the glass substrate will be absorbed by the PML. This essentially simulates a semi-infinite thickness of the substrate. Add a Mesh Override region from the Simulation drop-down menu. Mesh override regions are used to specify the mesh step size over a localized region in the simulation volume. Here we want to use a finer mesh to resolve the curved shape of the nanohole and the thickness of the gold film. Edit the mesh override region and set the mesh step size to 0.01 micron or 10 nanometer. Under the Geometry tab, set the geometry using the Based on a Structure option. Type Circle in the Structure field. This will set up a mesh override region over each of the objects named Circle. The structures inside the nanohole structure group are all named Circle. Click OK to accept the settings. To resolve the layer thickness, ideally we want the mesh lines to fall at the material interfaces of the gold film. Click the Show Mesh button on the toolbar to see the generated simulation mesh. In the Drawing Grid properties, turn off the drawing grid to better see the mesh lines. Because we are simulating a device where there are plasmonic effects, the results can be very sensitive to the meshing. The 10 nanometer mesh step size is the starting point, but for most accurate results, we need to perform convergence testing by trying finer mesh step sizes. Next, we will add and set up a plane wave source at normal incidence from the air above the structure. Add a plane wave source from the Sources drop-down menu. Set the source to inject in the backward direction along the z-axis. This means that the source will propagate in the -z direction. Under the Geometry tab, set the source x and y positions to 0 and spans to 0.5 micron. So the source covers the full area of the simulation region. Set the z position to 0.3 micron, so the source injection plane will be located in the air above the structure. Under the Frequency Wavelength tab, the source start and stop range are already set to 0.4 to 0.7 micron, which is the range that we're interested in. On the right, we can see the automatically generated source pulse over time, as well as the spectrum of the source pulse. You can click and drag an area on the plots to zoom in. Next, we'll set up monitors to record data from the simulation. We will be using monitors to record the refractive index profile, reflection and transmission spectrum, electric and magnetic field profile, and a movie of the time domain fields. Start by adding a refractive index monitor from the Monitors drop-down menu. Edit the monitor, and in the Geometry tab, set the monitor type to 2D Z normal. Set the x and y spans to 0.5 micron, and the z position to 0.05 micron, so that the monitor is within the gold film. Set the monitor name to XY index. Now add another refractive index monitor to see the field profile in the XZ plane. Set the monitor name to XZ index. Under the Geometry tab, set the monitor type to 2D Y normal, and set the X span to 0.5 micron and Z span to 1 micron. You can see the monitors in the viewports outlined in yellow. It's fine for the monitors to extend outside of the simulation region. Data is only recorded within the simulation region, so the results returned are automatically truncated by the inner simulation region boundaries. With index monitors, you can view the index preview result before running the simulation. To see this, right-click on Index Preview in the Result View window and visualize it. Here, I can see a hole in the gold layer as expected. The resolution of the curved surface of the hole is limited by the mesh step size. Next, add a frequency domain power monitor to measure the reflection spectrum. I can drag the monitor to resize or move it. I'll drag it to a position above the source to measure the reflected fields. Edit the monitor and set the name to R. To set the number of frequency points to measure over the source wavelength range, click the Set Global Monitor Settings button and set the number of frequency points to 50. Click OK to accept the settings. Click the Duplicate button in the toolbar to duplicate the R monitor. To use the duplicated monitor to measure the transmission spectrum, drag the monitor position into the substrate region. Edit the monitor and set the name to T. Add a frequency domain profile monitor to measure the field profile in the XZ plane. Getting the field profile at 5 frequency points is sufficient for this data. Select Override Global Monitor Settings and set frequency points to 5 to have this monitor only measure the fields at 5 frequencies. Under the Geometry tab, set the monitor type to 2D Y normal and set the X span to 0.5 micron and Z span to 1 micron. Set the monitor name to Profile. Add a movie monitor and set up the geometry to match the profile monitor. 2D Y normal monitor type, Y0, X-span is 0.5 micron, and Z-span is 1 micron. Under the General tab, you can set the resolution of the movie that will be produced and the field component that will be recorded. By default, the electric field intensity is recorded. Set the monitor name to movie. The movie file will be saved to the current working directory. You can change the working directory from the File menu. Now the simulation file has been set up, and you could run it at this point. But a final improvement that could be made here is to take advantage of the symmetry of the structure and the source to reduce the simulation volume that needs to be simulated. Since there is symmetry across the x equals 0 and y equals 0 planes, only 1/4 of the unit cell needs to be simulated, and the fields can be unfolded to the full unit cell. To set up the symmetry in the boundary conditions, edit the FDTD simulation region, and under the Boundary Conditions tab, select Allow Symmetry on all boundaries. Then set X-min and X-max boundary conditions to anti-symmetric, and Y-min and Y-max boundaries to symmetric, then click OK. The positive quadrant of the simulation region, which isn't shaded blue or green, will be the portion that is simulated, and the results will automatically be unfolded to the full unit cell. Using these boundaries, you will get identical results to using periodic boundary conditions, but less memory and simulation time is required. The rules for choosing which type of symmetry to use, symmetric or anti-symmetric, are covered in the FDTD Solver Region section of this course. As an additional exercise, try rerunning the simulation using periodic boundaries instead. You may want to save the simulation file now, as we will use the same file in the following demonstrations. In the next unit, we will cover the checks that should be performed before running the simulation.